Today she's going to be telling us about runtimes in data centers, in a data center context. And with that, you can take it away.
Okay. Oh, okay. No, okay. Hi. Uh, uh, so, um, so that's easier to remember. Yes, I'm co-directing Clarity Lab. It's quite a mouthful, but it stands for, you mentioned that, right? Cross-layer architectures and runtime. Um, uh, I thought it was such a cool idea when we came up with the name in the Seattle airport parking lot. When we just got our jobs. All right, so beyond research and creating research, we also created a human being in the last 3 years. Um, and this is little Zayden, he's 11 months old. Slight title we're supposed to actually do. We found out that he's not particularly interested in this. That was a very interesting keynote talk. Which is compiler for data centers and around areas that I've been working on in the last couple of years. Lab integrated cross-layer system. And one particular program that I'm going to talk about today. So scale, massive scale data centers, right? You actually optimize for there are, of course, many aspects of the data center. Well, those in the top, a resource allocation. In the last couple of years, that we have a bunch of publications. You could actually go to, obviously, my website on my website. Um, uh, Beyond data centers, one area started this for the research direction of so those applications that are powered by artificial intelligence. Those are actually very simple AI. Oh, I feel sort of applications coming out too, right? So that's just can actually power sophisticated apps. Two, one is called Sirius, and DOS intelligent application that we actually release and saying that it could be interpreted as Siri for us. So people bragging about my own stuff, but it's very, very computing as a service in data center, and how do you architect your data center? Often now to actually build a conversational system to actually doing a system that could potentially replace my job. Also, I'm also program for a lot of speed up. So very presented by our first PhD grad. And beyond that, as several work talk about sort of the interplay between. All right. So a little. You probably already guess warehouse scale that actually hosts 10. So you're looking at massive power, a small town to actually power this. When they actually released Siri build a data. I'm sure nowadays it's gonna get even more expensive. Instead of owning data centers, because your web services actually require thousands. Those actually applications run on thousands. Massive scale. Performance and cost, right? With one, it means high percentile latency is 10 milliseconds, meaning that means that 10 milliseconds, right? Very long tail distribution, meaning that there are your average latency curve. Then you're gonna ask, the very small percentage of the fan out style, meaning that you have a 2,000 leaf nodes to process. It's going to aggregate your tail of one leaf node performance. I have 1% of chance actually running at really low. Higher probability when you aggregate all those probabilities. Simple math, you could do probably 30–60% depending on how scale. So it matters a lot. a price tag at $1 billion, then of course high is, you build the data centers, you purchase food, right? One of the challenges is running a low utilization often that server not particularly energy efficient at low problem at hand. So utilization is. So of course I mentioned trade-off. I mentioned quality services. Data center utilization, but also actually guarantee the. This is a multi-core for this thing. On your machine, you can actually share some of the underlying. One application may kick the other app, or you're actually competing. The problem is data center or Google search, Microsoft search, or say as much. So when you actually co-run those applications, especially developer-facing applications. Right, so now you're actually really looking at how to utilization. The problem gets even co-location. So those are one is actually addressing CPU, and one is addressing. We talk about the protein code. So the state of we call unsafe co-location, where actually when you run application, quality service degradation. The solution you can throttle it and make it actually use less other application, right? So the high priority application running with the job 4, we could. And you may be thinking, oh, this is so easy. What a simple. There are actually a lot of consideration that go into that. Of doing things through OS do this, through compiler do this, through. Yeah, I could talk bad things. Most elegant solutions. It's a very. Everybody can thought about that. It's so heavy-handed. So what do? It's not like you could really actually let the application adapt themselves. Make applications adapt to its environment. I would just run really friendly, not taking. Wouldn't that be nice, right? Actually, execution environment. For example, there's load fluctuation. Many of us do, right? And there are code-runner changes. Requires a capability to adapt. Not really. This is such a dynamic code transformation is super expensive. And so what? Right beyond the overhead, there's actually addressed, including general purpose transformation power and extrospection. All right. Am I running out of time? So I'm gonna quickly go to the. All right. Oh yeah. Okay. So I'm gonna quickly talk about the solution then. So this is actually compare our technique with other techniques. DynamoReal is a state-of-the-art dynamic compiler, and the protein code I'm about to actually introduce is a low overhead system that's actually deployable. All right. So protein code means the protein means able to change frequently and easily, and it's a biological term. How do actually protein code actually address those key features? If you look at the difference between conventional dynamic compilation, actually, if you're actually interested in dynamic compilation, you should totally read original papers, but they're fascinating systems. But the way typically it's done is application running on the runtime. Runtime needs to actually basically have control during the entire execution. It's creating this code cache at the basic level or trace level. So basically, code will be actually generated in the code cache from this application, and it's actually runtime is taking control, and there's a lot of fine granularity control at the basic block level, and a lot of action between transitions between runtime and the code cache. So very heavy-handed approach to doing things. Any instrumentation is going to actually go back to the runtime, super heavy overhead. The protein code approach, if you don't understand, this is fine, but on a very high level, there's no fine grain control. The application can actually run continuously while the recompilation is happening, and the adaptability is statically stitched in. And the dynamic compiler, you can basically tune how much cycles you want to actually spend in a dynamic compiler, and it's going to actually, once the compilation is done, it's automatically asynchronously stitching to your application, and you can actually do recompilation really fast. All right, so I have 2 minutes to finish the talk. All right, oops. I think I'm gonna skip all the important, all the details. But the basic idea is we actually virtualize the control edges and creating this table. So and the runtime, the compilation will use the intermediate representation to actually recompile code, and it's going to put the new code into a code cache, and it's going to rewrite the EVT, the virtualization table, to tell the application, now I've finished the new compilation, and the code can be stitched into the. This is the rewriting, so the application can run continuously at the same time. So I'm going to quickly go to. This is why we actually have those satisfying those key features. But just a quick graph to show the overhead. So DynamoReal is a state-of-the-art, so it's running at 90% overhead without doing any recompilation. It's just basically running the system, and protein code is doing less than 1% overhead in this case. obviously didn't really practice the timing as a true faculty member. But anyway, the key idea of actually using this dynamic compiler is we could actually stitch in code that actually indicate to the microarchitecture, should I be actually aggressive with the cache usage or should I not? So with that dynamic compilation capability, we'll be able to actually, based on who you're running with and how much interference you're generating, recompile code and search for the search space and figure out how much cache pressure I could actually generate. And then basically dynamically tune your code to actually satisfy the quality of service. And with that, we can actually co-locate two applications together without actually generating a lot of interference and improve the utilization. And this is all achievable because the dynamic compilation has less than 1% of overhead. All right, so I could show you a lot of results, but let's not do that. This is the result I show is so much better than the prior work. But I just want to actually put the last slide in. This is a quote. I actually watched Kung Fu Panda 3, but I love this quote and I want to share with you guys. If you only do what you can do, you'll never be better than what you are. So that's just actually really stick with me. I think it's actually sort of one of my philosophies that you should always, when you get given a chance or have the opportunity to step out of the comfort zone, try something you will fail at, and that's the only way you can actually be really good at in the future. All right, thanks.
Somewhere else.
So then go into a lot of details. In the instruction set architecture, there are several instructions you could actually use to tell the microarchitecture that my memory access is not going to be a temporary access. So don't put it in the shared cache. So there are actually a lot of, this is actually supported by x86 and v8. So you could actually, there are a lot of those kind of instructions that you could give hints to the microarchitecture. So they will actually change the cache management for you. So that's why compilation is needed, because you do actually need to change your oh. So, oh. Mhm. Wow, that's interesting. I'm gonna have to read the paper, I guess.